Okay, so it's a great pleasure for me to introduce Fai Mak. I do not think Fai has visited JQI or CMTC before, which is well, virtually have visited CMTC. I mean, physically, right? Which is quite remarkable because I think most highly of his experiments. It's there's a group of 4, I'll call them young. They're all full professors, experimentalists whose work I follow. I can only talk about myself very closely. Fai is in that group. Pablo Herrero at MIT, Corey Dean at Columbia, and Andrea Young at UCSB. Anytime they post a paper or paper comes out, I mean, I like to hope they'll send me the paper, but sometimes they don't. I immediately read it completely, send it to the postdocs, and I'm saying it with no hesitation, and I don't read anything. I hardly read my own papers. And it really reminds me of 80s and 90s when I used to follow Stormer, Eisenstein, and Dan Sui and Aaron Pingzuk very, very closely. That was gallium arsenide. Now it's mostly Moiré graphene and Moiré transition metal dialpha-genides. And they're doing amazing work where topology, correlation, band structure, all these things come together. It's really like science fiction, all the variants on Hubbard model. Cold atom people thought that they had a monopoly on Hubbard model. These young solid state experimentalists show us not true. They can, do very interesting things. And it's like, condensed matter experiment now is at a peak that hasn't happened since the mid 80s because of these experiments. So anyway, Fai got his PhD. Well, amazingly, all these 4 people were at Columbia at one time, okay? Which is hard to believe. And I think they were even temporarily at the same time, right? 4 of you overlap, which is hard to believe. But, that was because of Philip Kim and Tony Hines, both gone. So it would never happen again. I told Andy Millis, he didn't like it very much. He got his PhD at Columbia, went to Penn State and became a full professor, I think, and then moved to Cornell, where he and his wife, they collaborate, very good collaboration. He's the transport person and his wife is the optics person, so the work is very solid. So Fai, please.
Thank you, Shankar, for the invitation and for the very generous introduction. Oh, how do I clamp this? That should be fine. Right? Oh, I accidentally pressed the button.
Let me check if it's okay.
You're fine.
I'm fine. Okay. All right. Okay. Yeah. Thank you again. It's my great pleasure to be here and talking to the colleagues and meeting with different people talking about science. And so today I will actually just talk about a class of material known as semiconductor Moiré materials, and I'll just tell you a few examples of how we try to, simulate some simple condensed matter model. And if time allows, I will talk about 3 examples. One is related to the Kane-Mele and Haldane model. The other is connected to the Kondo lattice model. Okay, so it's some recent development from our lab. All right. So just a very brief introduction of the component of the building block material that we use to make this Moiré material. Is a monolayer of this transition metal dichocarbonate, or the TMD semiconductor. So this is the structure of one of this layer. It has 3 layers of atoms with the middle layer of transition metal atoms sandwiched between the top and the bottom chalcogen atoms. Typically, this is moly or tungsten in the middle, and the sulfur, selenium, or tellurium at the bottom. And if you look top down, it's actually like a graphene lattice. It looks something like this, except that the A and the B sublattice sites are now occupied by different atoms. So the immersion symmetry is broken. And also very similar to graphene, that the electronic states of interest are near the K or the K prime value or the corners of the Brillouin zone. And then the simplified band structure of the material, something like this, you just have 2 copies of band gaps at the K and the K prime point. They are time reversal copies. And for the intrinsic material, the Fermi energy, which is the dashed line here, is located in the middle of the gap. Okay. So that's the building block material, just like how people make graphene Moiré materials. Starting from graphene, we make our Moiré materials starting from these building blocks. And just very similar to graphene, you can make a Moiré superlattice structure. You can use 2 of the same layer material. Then we call them a homo bilayer system. And then all you need to do is just to give a twist angle, and then typically you get a Moiré period about 10 nanometer-ish. And in this case, the Moiré period is proportional to 1 over the twist angle between the 2 layers. All right. Another way to actually make a Moiré heterostructure, which is somewhat different from graphene, is that now you can actually choose two different materials and then make use of the lattice mismatch between the two materials. For instance, I'm showing an example here of tungsten selenide on top of tungsten sulfide, and there's a 4% lattice mismatch between the two materials. So even you put them at 0 twist angle, because of the lattice mismatch, you also get a Moiré superlattice structure with period on the order of about 10 nanometer-ish. Okay, and the difference here is that the Moiré period is actually dependent not on the twist angle, but on the lattice mismatch between the two materials, which I denote as delta. All right, so these are the two ways, and I'll mainly focus on the second way here because it's relatively insensitive to the twist angles. That's something that we like it, and you can really see it in a TEM microscope. This is actually a collaboration with Dave Miller's group at Cornell, and you can actually see that this is a TEM image of another heterostructure, multi-telluride on top of tungsten selenide, and the small dots there, actually maybe not super clear here. You can see those are the real atoms of the original material. Then you can also see the interference pattern that produced this Moiré heterostructure. And because of the lattice mismatch to generate this Moiré superlattice structure, it's quite robust. You can actually see like hundreds of these sites are quite regular, forming a quite regular periodic lattice. Okay. And so, the emergence of the Moiré length scale is nice because that's actually a lot bigger than the original lattice constant A. So that there is a very nice separation, a natural separation of the high energy physics, which is governed by A, and the low energy physics, which is governed by the AM here. Okay, so in some sense, we can totally forget about the original lattice structure of the material and just treat the electrons with a certain band mass from the original material moving in this smooth periodic structure defined by the Moiré lattice. And what it does is basically that to reduce the big Brillouin zone in the original monolayer material into a small Brillouin zone or the mini Brillouin zone. Because of extra Bragg reflection from this Moiré superlattice structure, and then a series of mini bands will be produced by this Moiré lattice. Okay. Okay, so actually, interestingly, it was pointed out first by Alan McDonald's group in 2018 in the PRL paper that if you have a well isolated enough flat band in the system, say we actually can just treat. We only can look at this particular band at the top of the valence band here. If this band is well isolated enough, the low energy physics can actually be mapped to a triangular lattice Hubbard model that the Moiré superlattice structure is a triangular lattice. The electrons are trapped by these artificial Moiré atoms. The typical trapping depth is 100 to 200 milli electron volt. The sort of atomic spacing is about 10 nanometer now. And then the electron can hop between sites with an amplitude T. And if you happen to put two electrons on the same sites, they Coulomb repel each other with energy U. And they also can experience the intersite Coulomb repulsion of V. Okay. And to give you a sense of the energy scale, the T is typically 1 to 10 milli electron volt for the kinetic energy of the electron. And the U, you can estimate using the size of the 1-year orbital in this material is on the order of 100 milli electron volt. And the V here, you can use the Moiré spacing or the Moiré period and the dielectric constant of the surrounding dielectric, and then to estimate an energy scale about 50 milli electron volt for the V, nearest neighbor Coulomb repulsion. And you can see that the Coulomb repulsion energy scale actually dominates over the kinetic energy scale of the electron, typically in this kind of system. So we have a strong correlation physics quite easily to be seen in experiment. Okay.
So the hopping, is that an uncertainty or is that like can vary?
Depending on material, yeah. Depending on the Moiré period and depending on the applied electric field, sometimes you can, yeah. That's why I put the quote. And then for a triangular lattice, you have to multiply by a factor of 9 to get the bandwidth. Yeah. Okay. And things actually become a little bit more interesting. It's also from a McDonald's group, 2019 this case. If you actually happen to have two flat bands coming together, if the low energy physics cannot be just captured by one of the bands, instead you have to actually take into account the two bands. And things can become a little bit more interesting because you can also bring the two bands close to each other. You can even introduce a band inversion between the two bands, and you can actually generate topological bands in that case with a value-dependent Chern number of ±1, for instance. with this two-band model here. And in fact, the low energy physics of two-band model can be mapped to a model on a honeycomb lattice instead of the triangular lattice known as the Kane-Mele model that describes the nearest neighbor hopping T, the next nearest neighbor hopping T prime, which is like an effective spin-off interaction. And then you can also put an energy difference between the A and the B sublattice sites on the honeycomb here. That would be the on-site potential difference, which is tunable by an electric field. So the Hamiltonian in this kind of system, in this kind of two-band system, can also be continuously tuned by just simply applying an electric field, and that would just change the potential difference between the A and the B sublattice sites.
Could I ask you a question?
Yes.
Yeah, this is Bill Phillips, and this is a sort of an ignorant question from an atomic physicist. You're referring to these flat bands, but of course they don't look all that flat. So what makes something flat? That is, what has to be small compared to what for you to think of it as being a flat band?
Yeah, you sort of have to think that the kinetic energy defined by the Moiré period, right, which is basically h bar square divided by mass of the electron divided by the Moiré period square. That energy scale has to be comparable, or let's say have to comparable or bigger than the interlayer hopping term between the two layers, right? Because it's the periodic modulation of the interlayer hopping that produces the Moiré potential. So the Moiré, in some sense, the Moiré potential has to be strong compared to the kinetic energy defined by the Moiré period.
Okay.
Is that sort of clear? Then, you know, in that case, this you can think of it, this kind of the gap opened here is the hybridization gap that is created by the Moiré potential, and that has to be large compared to the just the folded band without that correction. Then the bands can be made really flat, right? If you know what I mean.
Okay.
Yeah.
So Bill, another way of thinking about it is that if you didn't have Moiré, and you look at the original system, those hopping matrix element T will be electron volt. And it has come down to be electron volt. So it suddenly has flattened a lot. And then this comparison that I talked about makes it flat. But it's not exactly flat, because for exactly flat, you know, it should be zero, mass should be infinite. That's not going to happen.
Okay.
Okay.
All right. Okay, so this, if you have two orbitals, you have to use a two-band model to describe it. And then in this particular example, well, it's not always the case that the two-band is mapped to a Kane-Mele, but in this particular example, this two-band model can be mapped to a Kane-Mele in terms of the low energy physics. Okay, and recently we actually, this is actually the material that I will mostly focus on. I'll talk about all the different kinds of physics in just this one compound, which is a AB stacked molybdenite tungsten selenide. And how we prepare this material is just that we mechanically exfoliate, you know, two layers, and then we rotate 180 degrees and put them together, right? So they are sort of, that's why we call them AB stack, because we rotate them at 180 degree stacking order. And we just make use of the lattice mismatch to produce a Moiré period about 5 nanometer in this particular material. And it actually, the low energy physics can be mapped to a two-band model because the topmost valence band of the system of this entire heterobilayer, actually the topmost valence band comes from the moly orbital, and then the next valence band actually comes from the tungsten orbital. And you can imagine that if I use a electric field, perpendicular electric field, I create a Stark effect, and that can shift the relative band alignment between the moly band and the tungsten band. Okay. And it's shown by Liangfu and collaborators that these two bands actually corresponds to, I have some difficulty to control this mouse. These two bands actually corresponds to a triangular lattice. So the one-year orbital for these two bands, they both form a triangular lattice, but when combined, they actually form a honeycomb lattice structure, which is pretty much like the Kane-Mele model. And here, in this case, the nearest neighbor hopping T is actually an interlayer hopping, because it's a hopping between the bands from the two different layers. And then the next nearest neighbor hopping T prime, which is actually oddly in this particular compound, is bigger than T. It's actually the intralayer hopping only within the layer of that band. Okay, and in some sense that this T prime is basically producing this bandwidth of each of this band, and the T is smaller than T prime. So effectively, the low energy physics of these two bands can still be mapped to a Kane-Mele model. And then the interlayer potential difference, which is controllable by the electric field, is actually equal to the A and the B sites sublattice potential difference in this case. Okay, so then you can imagine if I just apply an electric field, then I can introduce a band inversion for these two bands. I can make this charge gap here, delta, to go to negative, and then I may have some chance to create topological bands or Chern bands with finite value resolved Chern numbers. Okay, so this is the, yeah.
So, like, was the AB stacking required for this type of
Yeah, the question is whether AB stacking is required to introduce. Yeah, actually, yeah. So the question whether AB stacking is really required. For this theoretical proposal, for instance, they are not considering AB stacking, they consider AA. I think what's really needed is that you need a two-layer system. Then the electric field can tune the potential difference between the two layer, and that if the one-year orbitals happen to occupy a honeycomb lattice, then that's corresponding to changing the AB side as sublattice potential. So AB is not really required, but somehow experimentally, we so far only found one example, which is AB, that works well to have this band immersion and the introduction of topological bands. Yeah, but I don't think it is required. Yeah.
So is it that AA stack doesn't work, or is just AA stack doesn't happen in the experiment?
AA stack should work theoretically. Just we don't find it in the experiment.
I mean, you just don't find AA stacking in experiment.
We have AA stacking, but they somehow don't work.
They don't work.
Yeah,
Okay.
yeah.
He's saying it has not worked yet.
Yeah.
You'll make it work.
It's always the experimentalist fault. Yeah.
No, I mean,
we don't find it, right?
I mean, it might be there's a reason that it doesn't work. And
Yeah.
Maybe the parameters are wrong. Maybe the effective parameters.
Yeah. Well, or maybe actually it's triangular instead of a honeycomb or something. Yeah.
you find AA stacking or AB stacking?
Oh, it's just because each layer is a threefold rotation. It breaks the inversion symmetry, so that there is a difference of you put like the you can think of it the each monolayer is like a triangle. It's just AA is that you put the two triangles on top of each other, but the AB is just that we put one triangle to be like that. Yeah. So that's sort of connected to the honeycomb you sort of can see, right? Yeah. Okay, so this is our typical device structure. We studied dual gate devices. This is our heterobilayer, this sandwich between the hexagonal boron nitride. They are very good insulators that's used as gate dielectric. And then we also have the top and the bottom gate electrode. And we have two gates, so we have 2 degrees of freedom. We can independently tune the total filling factor or the total electron density within this heterobilayer. Or we can just apply a vertical electric field without changing the doping density in the bilayer, and that sort of tunes the band inversion and the band structure in the heterobilayer. And we also put multiple electrodes into this heterobilayer structure to form like a Hubbard device, for instance, shown here. And we can just pass a current and measure resistance and Hall resistance in the material, which I'll focus on. And you can also shoot laser in the middle of the device to do some optical spectroscopy. But anyway, this is sort of the general setting of this kind of device structure. And the important thing here, I'll come back over and over again, is that there are 2 gates. We can independently tune the electric field and the filling factor or the doping density in the material. Okay, so this is the outline. I don't need to go through all of them. I just depend on the time. I will first talk a little bit about the quantum spin Hall effect in this system and how we by breaking the time reversal, we also actually realize some Haldane physics. And the second example I will talk about is actually how we realize an interaction-driven Chern insulator. We call it topological MoTe insulator. And then finally, I will, if time permits, I will tell a little bit about some of the recent developments that we are looking at the Moiré Kondo lattice in this system, that we try to put one layer with just a lattice of local moment, and then another layer with just itinerant carriers to realize the heavy fermion physics in that system. Okay, it's all happened. All examples I talk about happen only in this one single material, which is the AB stack molybdenum tungsten selenide. So I don't switch material. So first of all, let me just talk a little bit something simpler. That I'll look at filling factor equal to 2, meaning that 2 electrons per Moiré unit cell. That we put 2 electrons per Moiré unit cell. We fix at that, and then we just tune the electric field in the system. So for that, what that means is actually that before band inversion, the Fermi energy, which is this dashed line here, is located between these 2 bands. And then once you apply electric field, you may invert the band, but the Fermi energy is still located inside the band gap. Then you can actually generate, you can turn the system from a band insulator to a quantum spin Hall insulator. Okay. And this is a transport experiment that we measured the 4-point resistivity as a function of the electric field, keeping nu equal to 2. And this is the measurement geometry shown at the top. Then we just pass, current in the longitudinal direction, and then we just measure this 4-point voltage here. Okay. And the other 2 sides of the electrode are also grounded. So now you can see the data at the bottom, which just shows the resistivity at different temperature. And this is the band inversion point, this particular electric field near 0.42 volt per nanometer. And before band inversion, you can actually see that as we decrease the temperature, the resistivity just goes up, typically diverge. Also very typical of a band insulator. This is in log scale. And after band immersion, you actually see that the resistivity first increases with decreasing temperature, but then it just tends to saturate to a value about 85% of H over 2E square of the quantum resistance. This is about 13.5 kilo ohm or something like that. It's not very clear in this log scale, but you can actually see that the resistivity sort of saturates with temperature, and then it also saturates with electric field. You can see an electric field plateau that the resistivity is nearly independent of the electric field after band immersion, which is totally different from the behavior before band immersion. Okay, so it's suggested that we actually get a topological state after the band immersion. So to further convince you that that is the case, we measure on the same device, but just slightly change our measurement configuration. Instead of a standard 4-point measurement, we actually try to force the current to go through the bulk of the material. So we bias AC in one of the electrode here and collect the current from the other side, but we ground this additional 2 electrodes. So we make sure that the current that we measure from the material really go through the bulk of the material without going through the edge. So it's like an effective Corbino, this type of measurement. And when we measure the 4-point resistivity, in this case, we measure the voltage drop across these 2 electrodes. When we do that, you actually can see that the resistivity as a function of the electric field after the band immersion, it keeps going up with decreasing temperature, right? When we access the bulk resistivity of the material, it just acts like a proper insulator. It does not show a plateau anymore. It just keeps going up with decreasing temperature. Okay, so yeah.
The gap is about 10 Kelvin.
The gap is about 1 milli electron volt ish.
Okay.
Yeah.
From the temperature.
Yes, it's about that value. Yeah. And yes, and we also check actually the spin quantization axis is really the outer plane by applying in-plane magnetic field. And so actually agrees quite well with the expectation that we get a quantum spin Hall insulator described by the Kane-Mele model before time reversal symmetry is broken. So one question we have is that can we just break the time reversal symmetry by applying a small outer plane magnetic field, then to reduce the system to a Haldane Chern insulator? So that's sort of the idea by just breaking the symmetry and sort of split the 2 copies of the Haldane and just retain 1 copy left in the system. And it turns out that the band structure of this particular A-B stacking of material is just ideal for doing that. So here is the band structure of the A-B stacking. What's so unusual about this is actually that if you look at the Moiré band, which is the green band here, from the K and the K prime valley, and the spin and the valley are locked because of the large spin-orbit interaction in the material. You can see that for the Moiré band, the K valley is spin down, and then the K prime valley is actually spin up for the Moiré band. But for the tungsten, it's actually totally opposite because of the A-B stacking. We rotate by 180 degrees, right? So actually for the tungsten, it's spin up for the K and spin down for the K prime. And what that means is actually that once we apply a magnetic field to the system, the K value will actually get a positive Zeeman effect that the gap would enlarge. And then the K prime value actually would develop a negative Zeeman effect, the gap would decrease, would just shrink, okay? So then you have an interesting scenario. Let's say that we tune our electric field, just make the gap to be very small. Let's say that just immediately after band immersion that we have a small gap quantum spin Hall insulator. Then we apply a small magnetic field to the system. One valley will just acquire positive Zeeman energy. The other valley actually acquire negative Zeeman energy. So we actually will enlarge the gap at the K prime and make the gap at the K smaller, and until they actually invert after a critical magnetic field. That after this band immersion, the band at one valley actually become topological trivial, while the other band actually still remain topological non-trivial. Okay, they still Chern band at the K prime valley, but they are not Chern band at the K valley anymore. So in the real space picture, what's really happening is that if you apply this magnetic field, you start with a pair of helical edge states for the quantum spin Hall insulator. Then near this critical point, one copy of the helical edge state actually get pushed to the bulk. And then after the reopening of the gap again, we just have a chiral edge state left, the chiral copy left in the system, and it's a Chern insulator after this. Okay. So this is the data. We try to keep at the band inversion point here because the gap is closest to the critical point. The gap is the smallest. And then we just look at how the Hall resistance and the longitudinal resistance depend on the magnetic field. And you can actually see that once we turn on the magnetic field at around 1 Tesla, our XX already dropped to a very small value. And then the Hall resistance actually goes up very quickly and finally reach about the quantized level at about 1.5 Tesla of magnetic field. And so that's consistent with this picture of that, you try to split the copy of the Kane-Mele quantum spin Hall insulator and then into a Haldane-Chern insulator by breaking the time reversal symmetry in the system. You can also park at a particular magnetic field and do a temperature dependence. You basically see that the resistivity indeed drops to nearly 0 at low temperature, and then the Hall resistance just go up to nearly the quantized level. And the energy gap for this particular system, the Haldane-Chern insulator, is about 3 Kelvin in this case from the temperature dependence. Okay. All right. So
Excuse me, Mark, yeah, could we go back to the previous slide again? So are those, sorry, are those little wiggles between 2 and 3 Tesla real? Are they interesting?
Oh, you mean this thing?
Exactly.
I think this may not be real, but actually what's real is that this goes up again.
Yeah.
Here. And the reason that it goes up again is actually that a high enough magnetic field. That's why I always want to say that we introduce at a low magnetic field, because at high magnetic field, you can see the series of Landau bands coming out above roughly 3 Tesla. Then the bands are inverted, you get a series of Landau levels coming out, and the Landau levels will cross and anti-cross, right? So that's why we actually get those things coming out again. So you actually can go up and come back down again because of the Landau levels. So I don't think those are real, those wiggles, but that goes up again and come back down again at high enough magnetic field. Those are real.
When I look at the red curve, I look at the red curve and I see that little blip at about 2.4, 2.5.
Yeah.
On the black curve, there's it's not as big, but there's also a little blip there. So I'm wondering.
Yeah. It may be related to this device only, but yeah, I think it's not. Let me put it this way: it's not reproducibly seen in all different devices. Yeah.
Okay.
But those are, the going up again at high magnetic field. Those are reproducible in different devices. Yeah.
Thanks.
Okay. So a quick summary of what happened at Nuclear 2, which is mostly single particle physics. I hope I convinced you that we have demonstrated tunable band immersion that makes the system a quantum spin Hall insulator. And then by applying a small magnetic field that breaks time reversal, you can actually sort of split the Kane-Mele system into a Haldane system that produces a Chern insulator with a quantized Hall effect. Okay. And it would be interesting to actually really push to the 0 magnetic field limit if we can proximatize the material to a magnetic material, or for instance, shining circularly polarized light or something to really actually split the Kane-Mele in this case to produce the Haldane-Chern insulator by finding some other ways to break the time reversal.
Is it possible to gap the quantum spin Hall insulator with the edge with a magnetic field yet in this material?
Actually, it's interesting that you apply an in-plane magnetic field, you kill the edge state because the spins are Ising-like spins. So the spins are like quantized in the outer plane direction. You apply in-plane magnetic field, you introduce this spin mixing between the two channels, then you kill the helical edge state. But when you apply outer plane magnetic field, it doesn't do much.
So the in-plane work, because I know in many materials this has been previously, like mercury telluride or something, it has been difficult to kill, or I think the way we do is experiments on indium arsenide, I don't remember the semiconductor. It was difficult to see the insulating phase.
I think the claim is that if I understand correctly, the previous materials may not be quantum spin Hall, they may just be 2D-TI.
Exactly.
It's protected by time reversal.
Yeah.
But here it's quite likely it's a quantum spin Hall. Right. That's why there's a very large difference of comparing in-plane magnetic field and the outer plane magnetic field.
But I was worried that the two edges also live on different values, which is why the hybridization might not be very effective. But you're saying it works in this case.
Yeah, you apply in-plane magnetic field, you still some mixing it. Yeah, you create some mixing.
The RX goes to 0.
No, sorry, the RXX goes up because the bulk.
Sorry, it goes up.
Yeah,
sorry,
yeah,
I mean,
yeah.
It goes up.
Yeah.
Goes to
the conductivity goes to 0.
Conductivity.
Yeah. Okay, so next I'll talk a little bit about related to correlation. I'll talk about interaction-driven Chern insulator. In this case, actually, you don't need a magnetic field. Everything is stabilized by interaction. So let's go back to this picture here. I will be talking about filling factor equal to 1, which means 1 electron per Moiré unit cell. Before you turn on any interaction and before band immersion, that corresponds to the Fermi energy cutting through the middle of the Moiré band. Okay, so it's a half-filled band, and you would expect it to be a metal without any correlation, and it's a Fermi liquid. And of course, if you turn on a strong correlation, the Moiré band, you expect it to split into the lower and the upper Hubbard bands. And as a result, the Fermi energy now is located inside the gap of this lower and upper Hubbard band. And the lower and upper Hubbard band is separated by energy scale on the order of the on-site U. But your electric field can also bring the tungsten band closer, right? And in fact, you can actually reduce the charge gap to be smaller than U. Then it's a charge transfer insulator in this case that, the charge excitation is from the lower Hubbard band of the Moiré to the tungsten selenide Moiré bands. Well, after band immersion, of course, without any correlation, it's still a half-filled, a topological band. It's still a Fermi liquid. But of course, with correlation turned on, you may expect that the energy gap still opened up at the Fermi energy, and you may have some chance to get actually an interaction-driven Chern insulator. I think people also call this a topological MoTe insulator because it's a Chern insulator driven by interaction. So indeed, if we tune our system to just after band immersion, and then tune the filling factor to equal to 1, you actually see that boom, suddenly the Hall resistance gets quantized at 0 magnetic field. So this is a Hall resistance data on the left. At different temperature, you can see that below about 2 Kelvin, the Hall resistance is nicely quantized to H over E square. And then at the same time, the resistance data, the RXX data on the right here goes to a very, very small value at low temperature. Okay, so these are the typical signature of a Chern insulator with a vanishing RXX and nearly quantized RXY near 0 magnetic field. And you can also see a nice hysteresis loop with the magnetic field that shows really that ferromagnetism is developed, and the time reversal symmetry is spontaneously broken. Okay. Well, you can also tune the electric field by keeping the filling factor fixed equal to 1. And this is the RXX map as a function of the electric field at different temperature. And the Chern insulator only happens in this small phase space here. You can actually see that the RXX drops significantly with decreasing temperature, and that's corresponding to the onset of the chiral edge state transport, and that's why the RXX drops significantly at here. At even higher electric field, it actually turns into a semi-metal. At lower magnetic field is a charge transfer insulator, is topologically trivial. So that's why the resistance just diverge with decreasing temperature. So everything is tuned by an electric field going from a charge transfer insulator to a Chern insulator, and then to a semi-metal. Okay, so next, what I'm going to tell you is actually that we try to measure a little bit more carefully of the thermodynamics around this MoTe charge transfer insulator to the Chern insulator transition here. And let's see what we can actually learn from this thermodynamic measurement. Okay, so to do that, let me just tell you a new technique that we recently developed, which is actually using optical method to measure the chemical potential, to directly read out the chemical potential of a sample. So this is our device structure, which is a little bit more complicated compared to the previous device. We have our sample of interest here, and we also have top and the bottom gates. All those white space region, they are just boron nitrides. They are understood as boron nitride. So in addition to this top and the bottom gate, we also put a sensor in between the bottom gate and the sample. Okay, and the function of the sensor is actually that we try to vary the bottom gate voltage to try to fix the sensor to a reference point, to a fixed reference point. And if we can do that, actually, the sensor here will provide a bridge and to help us read out the chemical potential of the sample simply by just, using the backgate voltage that we apply to fix the sensor at a fixed point, and then the bias voltage between the sensor and the sample. These two voltages, when combined, can actually be shown to be related directly to the chemical potential of the sample. And this ratio here is just the geometrical capacitances between this layer and that layer, okay? The bottom gate and the sample to sensor distance there. So, and that ratio can be experimentally calibrated very precisely. So what we need is basically that just to read out the bias voltage that we apply to the sample from the sensor, and also read out the backgate voltage to keep the sensor at a fixed point. Then we can immediately get the chemical potential of the sensor, of the sample. All right, and we are not the first one to actually realize this. Is actually Emmanuel Tutuk's group published a paper, PRL 2012, that first realized that you can actually use this method to read out the chemical potential. And in their experiment, they use a graphene sensor to read out a graphene sample. So a natural reference point for the graphene sensor would basically to put the Fermi energy exactly at the Dirac point, right? And you can monitor that by just measuring the resistance of the sensor. So it's actually a global measurement. It's because it's a electrical measurement through this entire sensor layer to read out the chemical potential from the sample. And this is an example. You can see the chemical potential as a function of doping. In a monolayer graphene, you can see the characteristic square root dependence of the chemical potential with doping. It's a global measurement because it's an electrical measurement on the sensor. So what we do here is actually we replace our sensor with a monolayer of this semiconductor. And instead of using transport to read out the chemical potential, we use optical means to read out the chemical potential. A natural reference point for this two-dimensional semiconductor is basically to keep the Fermi energy exactly touching either the conduction band edge or the valence band edge, right? And then we shoot light onto the sensor and look at the basically the absorption or the reflection contrast in the sample. And once you actually, we are looking at this particular interband transition in the sensor. And once you push your Fermi energy by applying the backgate voltage to just near the band edge, you can actually see that suddenly the reflection contrast of the materials would exhibit a very sharp step-like function in the system. So that provides us a very nice reference point that in the middle of this step, that corresponds to, when the Fermi energy is located just touching the band edge of the system, okay? So in our real experiment, what we do is actually that we use our sensor and the top gate as two gates to actually tune the filling and the electric field in the sample. And the bottom gate is actually just to keep the sensor at this fixed point through a feedback loop from the optical readout. Then we can directly read out the chemical potential in the system. And as a local probe, we can easily do chemical potential imaging as well. And I will show you an example. So here is the chemical potential as a function of the filling factor. Again, filling factor 1 is 1 electron per Moiré unit cell. And this is the chemical potential at different electric fields. So you can actually see that this is before the system gets to the band edge. When it reaches the band edge, there is a peak here, and then the chemical potential drops. And there's a little jump at 1/3, which is a generalized Wigner crystal state. And then there's another chemical potential jump at 1. Those are actually the MoTe state or the charge transfer insulating state. And with increasing electric field, you can also see that the gap at filling factor equal to 1 closes, you can no longer see the chemical potential jump, because with the electric field, you just invert the band, it becomes a semi-metal. Okay. So a few things I want to notice, that there is this black dashed line around this electric field. When you push up the electric field further, there's a spontaneous magnetic circular dichroism signal coming out from the sample that signifies a time reversal symmetry breaking, and that's where we actually get the Chern insulating states. So above this electric field, we get a Chern insulating state, and push the electric field further, we close the gap. And also, I would like to notice that the chemical potential actually keeps dropping with increasing density. That means a negative compressibility in the sample. It's very typically seen in all this Moiré system that the net compressibility is negative. And finally, you can just read out the gap size of the insulating state by just looking at the size of this jump in the chemical potential. So you can directly read out the chemical potential jump. So here I'm showing a movie of the chemical potential map as a function of the filling factor in this sample. We pick a particularly inhomogeneous sample to actually show that this works, the technique. And you can see that near filling factor 1, there's a quicker change because of the gap size. There's a charge gap in the system. But yeah, you can easily acquire a chemical potential map with about submicron kind of resolutions, spatial resolution. And from this map, we can also try to induce, the disorder in the Moiré density, which is about 10% variation in the system, and as well as the gap size. Actually, the gap size will vary quite a lot more, way more sensitive compared to the Moiré density. So you change the Moiré density a little bit, the gap size actually can change a lot. Okay, so let me just go back to a single point, a measurement. You can directly read out the gap size as a function of the electric field. You can actually see that the gap size just continuously decrease, and then just to 0 about this electric field here, okay? And where is the Chern insulator? So we can also do simultaneous magneto-optical measurement on the same sample to look for spontaneous time reversal symmetry breaking, in particular, the magnetic circular dichroism signal from the sample. And you can actually see that this is the turn on of the magnetic dichroism signal. So that's the time reversal symmetry breaking. And above the first orange dashed line here, we actually get a Chern insulating state with spontaneous time reversal symmetry breaking. And then the Chern insulating state is gone with further increase in electric field because the system turns into a semi-metal. But the punchline here is actually that you can see that when the system goes from topologically trivial, which is charge transfer insulator, to a topological non-trivial state, which is a Chern insulator, there's no charge gap closure in this topological phase transition. The Chern number is changed from 0 to 1, but the charge gap actually does not close in this topological phase transition. It just gets closed at the higher electric field that when the system turns to a semi-metal without time reversal symmetry breaking. So at the state with time reversal symmetry breaking, there's no charge gap closure. And that's sort of odd because most of the topological transitions that we know.
This slide that you showed, it's you have the ability to do local measurement.
Yeah.
So this was for a specific point, or you just average over the sample?
This is for a specific point. Actually, we find a point that is a, let's say, with the strongest MCD signal with the most robust Chern insulating state. But this is not like a very difficult to find. I mean, you can find multiple points on the sample to be like that. Yeah. Because at different points of the sample, you also have inhomogeneity at the band immersion electric field, right? So you can imagine at this point, the band inverts at this particular electric field, but at some other point, it inverts at a slightly different electric field. So that's why this sort of technique with very local measurement helps us to really get this thing out. Yeah. Yeah. Okay. So no gap closure is somewhat unusual. But in the literature, there are actually different theoretical papers talking about the possibility of a topological phase transition without gap closure. It typically involves change in the symmetry of the system, which I don't, totally understand. But quite likely, what's happening here is that it's a possible weak first order topological phase transition in the system. Then the jump in the charge gap at the topological phase transition, which in that scenario, you would actually expect a jump at the charge gap around this boundary here, is sort of smeared out by the disorder. But it's also somewhat surprising that you actually see that the charge gap really evolves smoothly in this transition. So I think I would say that at this point, we really still don't know, the experiment. But you can actually see that there are now multiple theory papers, including one from Shankar, that are talking about. I didn't update update yet. Yeah, so really talk about the possible, first order phase transition, the first order.
It's a very interesting observation, particularly if it's not disordered.
Yeah.
If it's disordered, then it's disordered. But if it's not disordered, something.
Maybe some intermediate state or something that we are missing. Yeah, yeah.
Data are clear, right?
Yeah. Okay, so that's for this part. Any other question? I
had a question. So this is in your favorite material, my favorite material also. But this may be generic in other meaning, for example, a homo bilayer. Do you think it is possible twisting things? I mean, what's your intuitive feeling?
It is also possible for homo bilayer, but I actually don't know what determines under what situation you will have a topological phase transition with gap closure, and sometimes you don't have a gap closure.
The topological phase transition has not been seen there, right? I mean, in the homo bilayer.
We have seen actually from quantum spin Hall to an anti-ferromagnetic insulator, but not this type. Yeah. So I think it's probably it has to be interaction driven to have something like a topological phase transition without gap closure. Yeah.
I mean, both are described by similar Hubbard model, right? So it could be a parameter question.
Mm-hmm. Yeah. So it's good to look at different systems if we have different parameter range. Yeah. Okay.
I have an experimental question. What is the material used for sensor? I'm assuming it's a different temperature, have a different.
Actually, we used a tungsten selenide as a sensor also. The reason is actually that once the tungsten selenide in proximity touch with the Moiré selenide forming a Moiré period, its resonance already shift to lower energy. So even we use a monolayer tungsten selenide sensor, it's totally fine. And the reason we choose monolayer tungsten selenide is just because that step edge, is very sharp, and it really just improves our sensitivity on the chemical potential sensing. In fact, it works really well that the noise of the chemical potential measurement is about 20 microvolt per root hertz, even for DC measurement. So it's actually a really sensitive chemical potential sensing method. I actually don't think I have much time left, but maybe I just give you a. Okay. I will just give you a flavor of how we can also try to engineer the system to a Moiré Kondo lattice. And the basic idea is actually quite simple, although when you look at the experimental data, the phase space is a little bit complicated. The basic idea is actually we go back to the charge transfer insulator before band immersion. Then the strong correlation will open up a MoTe gap for the Moiré layer. Then you bring the tungsten selenide band closer to the lower Hubbard band of the Moiré layer by an electric field. Then the filling factor 1, the Fermi energy is here. Then the Moiré layer will actually support a triangular lattice of local moments because it's in a MoTe insulating state. Okay, and you can actually really see the effect of this presence of this triangular lattice of local moments by measuring the temperature dependent magnetic susceptibility. You can actually see that it follows very nicely the Curie-Weiss law, which is really the signature of the presence of a lattice of local moment in the system. And in fact, by fitting to the Curie-Weiss law, you can also get a measure of the exchange energy scale in this kind of system. So it's at least consistent with the Anderson super exchange, which is anti-ferromagnetic. We have a negative Curie-Weiss temperature in this system. Okay, and then the idea now is actually to dope additional carriers in the tungsten band. So to look at a doped charge transfer insulator. And from the calculation and also from the experiment, from band structure calculation and from our experiment, that the tungsten band actually is much less flat compared to the Moiré band. So in that respect, it's like itinerant carrier in the tungsten layer. So once you do this, you actually end up with the situation that if the MoTe gap of the Moiré survive with the doping, then you have a lattice of triangular lattice of local moments, and then with itinerant carriers on only the monolayer of tungsten selenide. And the two types of carrier can exchange couple through the Kondo exchange, which one can also estimate using the outer plane tunneling constant T perpendicular divided by the charge gap of the system. So actually the Kondo exchange is also totally tunable. So it's actually of an Anderson type of a super exchange for this Kondo exchange mechanism. And in addition, the presence of a free carriers in the tungsten layer would also produce an additional RKKY exchange between the local moments in the system, in addition to the Anderson exchange. Okay, so effectively, you realize a Kondo lattice model by just doping a charge transfer insulator. The question is, where is this doped charge transfer insulator in the phase space that we have in order to realize this Kondo lattice? And this is the schematic electrostatics phase diagram. The vertical axis is the interlayer potential difference, which is tunable by the electric field continuously. And the x-axis is the filling factor, is also continuously tunable. I told you about the topological phase transition from a band insulator to a quantum spin Hall insulator at filling factor equal to 2. Happens around here. And I also told you about, how we introduce a topological phase transition from a charge transfer insulator to a Chern insulator along filling 1. And then by looking at this phase diagram, then you would expect actually the Kondo lattice physics to appear just doping on the right a charge transfer insulator where the charge carriers will go to the tungsten layer. And it makes a certain slope because of the finite charge density of the finite electron density of states of the tungsten layer. Okay. So that's where we expect we have a Kondo lattice in the system. And another control experiment nicely that we can do is actually by just looking at a doped charge transfer band insulator. And in this particular region here, the MoTe layer actually is kept at filling factor equal to 2. So we have 2 electrons, they form spin singlets at each side here. And then we dope additional free carriers into the tungsten layer. So that's corresponding to this region here, okay? And we would expect no Kondo physics in the system because we just totally quench the local moments. Yeah.
This is the cartoon, or this is like the middle line? Because when you increase the confining potential, at the same time that you're increasing U, you're also increasing the Moiré subband space. So
you mean this electric field here?
yeah, so the filling factor 1 as a function of interlayer potential.
Yeah. So in principle, it does more than just changing the interlayer potential difference. It may not change the U too much, but it probably changed the bandwidth of each band. Yeah, you change the bandwidth a bit more. You can change also the delta in that case. So this is really just highly schematic. Yeah.
The delta is getting larger than I want.
Actually, going this direction, the delta gets smaller. The charge transfer gap with increasing electric field, the delta gets smaller. Yeah, and the delta is bigger at the bottom down here. So in some, actually, is that the MoTe gap is proportional to the electric field span in this vertical direction here. Okay, and then the Moiré band gap is actually proportional to the electric field span in this direction there. And actually, I can show you the data immediately. So this is the data at 13.6 Tesla. We just apply a very large magnetic field so that we can see the Landau levels. The magnetic field will just exceed all exchange energy scale so that we can clearly see all the Landau levels developed. So you actually can see that this is a filling factor 1, this is filling factor 2. You can see the development of the vertical stripes, which is actually only from the Landau level of the tungsten layer. And it's independent of the electric field, just shows that we are
It seems like we've lost the audio from the mic in the room. Maybe someone else on Zoom can confirm that.
Yes,
I
there's
can confirm.
audio. Yeah.
Thank you.
How about now?
Sounds like we're back. Thank you.
Okay.
Yes, good.
Something happened.
Alicia's magic touch.
Yes, fears. I have put it frozen. I have a question. Can you remind me the cycle energy at the magnetic field, 1.6?
It's about 2.5 milli electron volt. It's not a large energy.
Not a lot.
Yeah. Because the mass is heavy, so it's
yeah. That's why you want to get.
Yeah, you sort of need to get the sample pretty clean to see.
I
the
just want to
state.
ask you that question. That's
Yeah.
You have to worry about result about 2.3, does it? Okay, good.
Yeah.
Good.
Yeah, but I want to point out basically that you have this region with just vertical stripes, which you only have one Fermi surface, which is the tungsten Fermi surface. And then there's another region here around filling factor equal to 2. You also see the vertical stripes. So you sort of can basically divide that into this line that it actually looks a bit like the schematic that I showed you before. That here at filling factor 1, we start with a charge transfer insulator before band immersion, then we dope additional carriers into the tungsten. And then we only have one set of electric field independent Fermi cyclotron resonance in the system, right? And then this is starting from the band insulator at filling factor equal to 2. We just dope a band insulator, but not doping in the MoTe layer, but doping in the tungsten layer in that case. Okay, so these two are corresponding to these two different scenarios. One is with your Kondo lattice physics. The other is actually just a dope band insulator. You should not expect any Kondo lattice physics in the system. And then finally, I just want to mention that this vertical span in the electric field really shows that the MoTe gap and the Moiré band gap survive with, the Moiré band gap survive is not that surprising with doping in the tungsten, but the MoTe gap survived also with the doping in the tungsten. And that really, lays the foundation to realize the Kondo lattice physics. So now the gap survived, you may also ask, what is the mass of the itinerant carrier? We can do a temperature dependent quantum oscillation measurement. And it turns out that the mass is about 0.5 electron mass. And you can compare to a monolayer of tungsten selenide electron mass, which is 0.45. So you can actually see that in this particular system, for some reason, the tungsten nearly do not see the Moiré potential. It's like nearly just free carrier or itinerant carrier in the tungsten layer. But only the MoTe that has the strong Moiré potential that produces a lattice of local moments. So we have now two conditions. One is that the survival of the MoTe gap with doping in the tungsten, and the other is that nearly itinerant whole mass in the tungsten. So the two conditions come together would help us form a Kondo lattice. Okay. So I just quickly tell you that we actually do see heavy fermions. For instance, you can, just to quickly remind you that for Kondo lattice, there is a characteristic temperature scale known as the Kondo temperature, below which the Kondo singlets form. And if you have a lattice of those Kondo singlets, you have a lattice of local moments, you actually develop coherent transport and Fermi liquid behavior with the T-square dependence of the resistivity at low temperature. And you also develop a large Fermi surface because now the local moment is fully absorbed by the itinerant carrier. So before the absorption of the local moment by the itinerant carrier, we actually would expect a Fermi surface with doping of delta. Delta is the average number of electrons per Moiré unit cell to be less than 1. But once you form a heavy Fermi liquid, you actually would expect the Fermi surface, the size of the Fermi surface to become 1 plus delta, which is a large Fermi surface there. Okay, so these are the two things that we would check. We would check, the emergence of the coherence transport at low temperature, and the other is the change in size of the Fermi surface. Okay, so to quick, this is 1 plus delta. We keep a layer of local moment in the MoTe layer, and this is the resistivity versus temperature data at different filling factor. But the filling factor is that we only change the filling of the itinerant carrier. The local moment is always kept at a triangular lattice of local moment. There's no change in the filling of the MoTe layer. Okay, so you can see a characteristic Kondo temperature, below which the resistance drops significantly, and you also develop this coherent transport of a T-square dependent resistivity at low temperature, which you can fit by this formula here with the T-square dependence. This is at 2 plus delta. No Kondo physics should be there because 2 electrons per Moiré unit cell in the MoTe. You can still see coherent transport at low temperature, typical of a Fermi liquid, but you don't really see the presence of a Kondo temperature, that there's no characteristic peak temperature in the system like compared to filling factor equal to 1. In fact, the resistivity will sort of saturate when the temperature becomes comparable to the Fermi energy in the system. Okay, you can extract the mass by using a Kawasaki-Wood scaling because in Kawasaki-Wood scaling, it just tells you that the coefficient A here is directly proportional to the quasi-particle mass. For filling factor equal to 1, plus delta, you can actually see that this is the data. For filling factor 2 plus delta, this is the data here. The mass enhancement ratio is between 10 to 20. And since we determine the mass from quantum oscillation to be about 0.5 for the itinerant mass, we actually get 5 to 10 times of the itinerant of the free electron mass for the heavy fermions. Okay, so one last thing is about the size of the Fermi surface, because if I just tell you that, you may not believe me. But if I tell you the size of the Fermi surface, you probably will believe me. So here, again, I'm plotting the Hall resistance versus magnetic field for 2 plus delta case, which is the dotted line here. It's a negative Hall resistance, nearly weakly dependent on magnetic field. It actually is a Fermi surface of the whole Fermi surface is a negative Hall resistance. It's a small Fermi surface of just the delta carrier that is inside the tungsten layer. It does not have significant change with the magnetic field. On the other hand, for 1 plus delta, here you can actually see that the Hall resistivity change sign to positive means electron transport. It's actually electron transport of a Fermi surface of 1 minus delta, and that corresponds to a whole Fermi surface of 1 plus delta. So it's actually a large Fermi surface and a large mass here. And once you go beyond the critical magnetic field, the Hall resistivity drops to the 2 plus delta case. That becomes just the usual small whole Fermi surface with a Fermi surface size of delta here on this case. And immediately also you can see that beyond this magnetic field, the quantum oscillations comes out showing that the mass suddenly actually would just drop quite a lot. That we immediately see the quantum oscillations. So what's happening here with the magnetic field is actually that when the Zeeman energy from the magnetic field becomes comparable to the Kondo temperature, you just forcefully just break the Kondo singlets in the system, and then you decouple the free carriers from the local moments, and that's why the size of the Fermi surface will suddenly drop from a 1 plus delta large Fermi surface to a delta small Fermi surface here. Okay. All right, and we can also tune the electric field and tune the filling in the tungsten layer to actually continuously tune the Kondo temperature as well as the heavy fermion mass in the system. So that's sort of a nice thing that one can do in this continuously tunable solid state system. Typically in the quantum material, you have to grow a completely different compound, but everything can do in a single device. Okay, so just to conclude that, I hope I convinced you that you can actually play lots of fun games here. In this one single material, all you need to do is just to tune the 2 gate voltages, and then you can get Haldane physics, you can get MoTe physics, and you can get Kondo lattice physics. And so hope this is just the beginning that we actually find this a sort of simulator for condensed matter phenomena, and there may be other examples to be discovered in the future in this or other class of Moiré materials. And before ending, I would like to thank really the people doing the work. I share a lab with Professor Ji Shen at Cornell University, and Haldane work and the Kondo lattice work is mainly driven by this postdoc, Wenjing Zhao, in our group, and he's looking for a job this year. And Chern insulator was discovered by Tingxin Li and Shenwei Jiang of 2 former postdocs, and the chemical potential measurements were done by Yihang Zheng and Zheng Xiaoxia. Zheng Xiaoxia is a graduate student, and Yihang is a postdoc in our group. And we also acknowledge theory discussions from Liang Fu's group.
We've lost the sound again.
More questions. We have a lot of questions and more questions.
So do you see the in this Kondo story? Do you see the susceptibility, the magnetic susceptibility? That should also disappear, right, as you enter the Kondo singletary? I mean the J, the effective J that you measured in the triangular lattice Hubbard.
Yeah, we actually measure the MCD, which actually only probes the local moment response of the MoTe layer. There is a differential susceptibility peak at the breakdown transition here. So it's basically like before the breakdown, the magnetization sort of grows slowly, and then it has like a sharp growth. So differential susceptibility peak at that transition here, and then it saturates basically because you sort of break down the Kondo singlets, but the local moments still saturate, right? Because remember that the exchange energy scale between the local moments in this type of system is small. It's not like in the real system that they have strong exchange. You don't really saturate, but here we saturate already. Yeah.
Other questions, comments? Please.
So I think your Kondo physics was done in the charge transfer meeting where the MoSE2 layer has no spin ordering. I was wondering if you go into the quantum anomalous Pauling vector, then introduce layers into something like that. Do you expect to see any interesting things?
Yeah, the magnetic response, you're talking about like a slightly doping a Chern insulator, right?
Yeah.
Yeah. The whole response is certainly weird. And so we're trying to stay in a regime that we still sort of understand before band immersion. But yeah, it's a very interesting question of what if you go to the regime that you start with the Chern insulator, you dope it. That regime, we have data, but we don't really understand that much at this point, yeah.
Yeah.
Do you see like a change of Kondo temperature as function of the vertical displacement?
Yes, it's actually this data here. Oh, I'm going the wrong direction, sorry. So this is tuning the electric field at a particular doping. So the electric field sort of changed the relative displacement of the Hubbard bands and the tungsten band, right? So these two dashed lines is basically corresponding to the two edges, basically the edge of the tungsten band touching the upper Hubbard band or touching the lower Hubbard band. And so you do get a minimum of the Kondo temperature, but not really exactly in the middle. You can see asymmetry in the electric field dependence. In the simple model that people cook up, it's exactly symmetric. Touching the lower Hubbard band or the upper Hubbard band is exactly symmetric, but in experiment, it's not symmetric. And we believe that, you know, in experiment, it's just that the lower and upper Hubbard band in this system is not totally symmetric. So, yeah.
Let me ask you a question. This is about the last part of your talk, which I found fascinating because I didn't know anything about it. So the question maybe just reflect my ignorance. So as you know, there is a lot of discussion right now because of Andre Bernardin's, I think, seminal work in twisted bilayer graphene, that it's basically heavy fermion physics. You know, all the correlated phases come from there and so on. There, the Kondo part is not very important, but you think you started with Kondo and ended with heavy fermion. There we are starting with heavy fermion looking for Kondo. Can you just illuminate a little bit? I'm very confused because I just finished a 100-page paper with him, and I realized I didn't quite understand what I did. So because I could not connect it with what you are saying. So
if you don't understand, do you expect me to understand?
Why? Usually I think of Kondo as starting by heavy fermion going to Kondo. Here you start with Kondo. What am I missed something?
I would say that here is a bit more conventional. That yeah, we start
so
with.
We really have moments here.
Yeah, we have a lattice of well-defined local moments, and we can also measure the mod gap size, right? But that part, yeah, the statistic paraffina, yeah, I don't.
So that was you were starting with real moments. So
yeah, I start with real moments here. Yeah.
I didn't realize it's something that simple. Okay. Good. Somebody had a question. You want to interrupt? Please.
I guess I was wondering. You said that there was disorder in one of your plates, and so optically you can probe the point, but presumably electrically you're probing sort of average.
Yeah.
So how do you combine this? Because you were saying you look at a specific point.
Yeah.
You're using two responses. So
yeah. So those are the two different samples, and typically it's way harder to make this electrical transport samples. If they are like as disordered as I show you for the optic sample, then you cannot really measure anything too meaningful in a transport device because we measure globally throughout the entire sample. So those are just the totally different samples, and typically we shoot for really homogeneous sample for the transport measurement. Yeah. Yeah, those are actually quite uniform. I would say that you can look at how sharp basically each of the correlated insulating state is with doping. And typically when we dope by 5%, we get out of the Anderson localization regime. So about 5% of the Moiré density, we just get to, we go through, that's the mobility edge, yeah.
Okay, I will have to cut off the discussion because we have lunch waiting and so on. But thank you very much.
Okay.
This was a very simple.
Thank you.